Hello, everyone. The paper I shared is RefSR NeRF, towards high fidelity and super resolution view synthesis. We observed two limitations of NeRF that prevent it from achieving fast high resolution rendering. For the first flaw, due to the dense sampling strategy and frequent MLP queries, rendering a NeRF is agonizingly slow. As shown in table, even running on a high-performance GPU, it takes 10 seconds to render a low-resolution image, which becomes even more unacceptable when the resolution continues to rise. For the second flaw, NeRFs tend to lose high-frequency details in distant texture due to the isotropic filtering. This can be attributed to that MLPs perform poorly to regress the high-frequency details from uniformly sampled low-dimension 5D coordinates. Therefore, we propose RefSR NeRF framework that first learns a LR NeRF representation, and then reconstructs the high-frequency details with the help of a HR reference image. We observe that simply introducing the pre-trained models from the literature tends to produce unsatisfied artifacts due to the divergence in the degradation model. To this end, we design a novel lightweight RefSR model to learn the inverse degradation process from NeRF renderings to target HR ones. Extensive experiments on multiple benchmarks demonstrate that our method exhibits an impressive trade-off among rendering quality, speed, and memory usage, outperforming or on par with NeRF and its variants while being 52 times speedup with minor extra memory usage. NeRF samples rays corresponding to each pixel randomly and renders color information. However, the inherent nature of MLP leads to poor performance of NeRF in high-frequency scenarios. Conversely, RefSR extracts features of continuous pixels in the reference image to reconstruct high-frequency information of the LR. However, NeRF outputs random rays features, which exists gap with SR models. Therefore, we present a patch-based NeRF to connect the NeRF to the SR module in the training stage, as shown the top branch in figure. We first obtain the rays from a continuous region rather than stochastic selection. The final ray color is then obtained by the MLP and the volumetric integration. Finally, rendering regions are sent to the subsequent network to train the SR module. The formulation can be described as the equation, where A represents the sampled batching rays from training images in a continue region. Combined with RefSR, NeRF achieves considerable rendering acceleration and restore high-frequency information from reference images. However, recent works in the RefSR mainly focus on modeling the specific downsampling degradation procedure, none of which has explored this emerging but sophisticated degradation process caused by MLPs and NeRF rendering pipeline. Therefore, as shown in figure, we present a reference-based SR module to exploit reference images to super-resolve the LR images generated by NeRF model. The main considerations of our approach are how to model the downsampling degradation procedure between HR and NeRF's LR views, and to transfer high-frequency details from a content-consistent but misaligned reference image to the final HR image. Specifically, we design a two-branch network that thoroughly exploits detail-dominant and degradation-dominant information from the respective branch and fuses these two outputs effectively. The detail branch aims to transfer the high-frequency details from ref inputs. For the purpose of effectiveness, a HR reference image is sent to assist in detail restoration, and the degradation branch takes the LR and ref at low resolution as inputs to guide subsequent image fusion. The LR view of ref is synthesized by MLP with the ref camera pose as input. Table demonstrates the effectiveness of this module. DOTSR and TTSR are excellent methods in the RefSR task, while the former achieve state-of-the-art performance. In the case of pre-trained and scratch, these two methods are compared with our method. However, experiments show that these two methods are not suitable for downsampling degradation caused by MLP. This page shows the quantitative results for the LLFF dataset, with scales multiplied by 2, 4, and 8. We compared with bicubic interpolation, vanilla NeRF, and NeRF-SR approaches. For vanilla NeRF, in addition to training and testing models at high resolution, termed NeRF-HR, we also provide the model trained at low resolution and render at high resolution using spatial supersampling. Table demonstrates that our approach can outperform NeRF-LR and NeRF-HR in render quality, and be comparable with NeRF-based methods NeRF-SR while achieving considerable rendering acceleration. Specifically, for the test scale ×2, our approach achieves at least 5 times render acceleration with a slight degradation in render quality. For the test scale ×4, our approach achieves over 30 times speedup while keeping the comparable result of the state-of-the-art method. For the test scale ×8, the rendering quality of our method is superior to NeRF-HR, and the rendering speed is over 50 times faster than NeRF-HR. Note that the rendering quality of our method decreases slowly as the test scale increases, which means that our method is more robust when synthesizing high-resolution views. We compare the rendering quality, rendering speed, and memory usage of our method along with MLP-based methods and caching-based methods. We can see that non-caching methods except LLFF have a slower inference speed compared to the caching-based methods, while caching-based methods have a considerably high memory overhead, at least 62 times. LLFF meets both high rendering speed and low memory consumption but performs poorly. Therefore, there is a clear trade-off between the memory consumption of a model and its inference speed and quality. Our method exhibits an impressive trade-off among rendering quality, speed, and memory usage, outperforming or on par with NeRF and its variants while being 5 times speedup with minor extra memory and storage usage. Note that with the increase in resolution, our approach maintains high rendering speed and low consumption, while rendering quality decreases slightly. This page shows the visualization of different methods at the rendering resolution of 2K and 4K. Our approach produces accurate and precise textures on all tested scales. Bicubic and NeRF tend to have noisy and blurry renderings in cropped flower patches, the red rectangle, and leaves patches, the yellow rectangle, indicating that our method outperforms NeRF in high-frequency information restoration. That's all for my presentation. If you have any question, please feel free to contact me. That's all. Thank you.